So in class on Friday, we started talking about Le Chatelier's principle, and we're going to continue with that today, looking at a lot of examples of how Le Chatelier's principle kind of affects a particular reaction. So we've used this analogy in class for equilibrium. If we have a system that is not at equilibrium, then it will proceed until it gets to equilibrium, and then it will stay there. So we have it not at equilibrium. And then we get to some place where we're at equilibrium, and we see that things are changing. We have a dynamic situation, so we have people going in and out of the room, and so we end up with different people outside the room than were out there before, but we still have the same ratio of the 3 people outside and everyone else inside. And so this is kind of a standard definition of equilibrium. What we want to look at now is what happens when we do something to disturb that equilibrium. So what happens when we change the condition? So here we have a system that is at equilibrium, and we do something to change that. Maybe we turn up the heat inside the room, and so now it's getting too hot in here, okay? And so everybody's getting very hot, and so what happens is we change the shift. So more people go outside the room because they want to be relieved from that heat. We're relieving that stress on the system, and so they're going outside the room. So we end up with more people outside the room than inside the room, and so we are at a new equilibrium here. Okay. And then maybe it starts to rain. Our lovely little rain coming down. And so some of the people are still not willing to go back inside, but we get some people moving back inside because we now have some new stress on the system for the rain. And so even though it's still hot in here, it's kind of a balancing out between the miseries here. Do you want to be hot or do you want to be wet? And so again, we get back to some new equilibrium. So anytime we change the conditions, we can still be at equilibrium, but it might be a new equilibrium. So what we're going to look at are the different things that we can have happen that actually disturb and affect equilibrium. So we're going to talk about several things here. We're going to talk about changing the concentration of a reactant, changing the concentration of a product, and those will be increases or decreases. We'll talk about changing the pressure, whether we're talking about changing the volume of a container or addition of an inert gas, or we can look at changing the temperature, and we have a little bit of a errant line here. But we're going to look at all these different things and talk about how they affect a reaction. So the first thing we're going to look at is changing the concentration of a reactant. And so what I want to look at first is when I increase a reactant, and then we'll look at decreasing a reactant. And so what happens is whenever we have our law of mass action, we know that K is equal in this case to our CH3OH concentration, or we could be looking at pressures as well because we're dealing with gases, CO times H2 squared. So we have our law of mass action here. And what happens is if I increase the amount of carbon monoxide, if I increase that amount, then my denominator is getting too big, and so we're no longer at equilibrium. In order to restore that point of being at equilibrium, I've got to change something. I need to get rid of some of that excess carbon monoxide was added, and the way I get rid of the excess carbon monoxide is I use some of it up. So I'm also going to use a little bit of H2O, so that's going to decrease, and I'm going to see an increase in the formation of CH3OH. So if I add a reactant, I favor the formation of products. Now, just the opposite occurs when I decrease the amount of reactant. So if I take away some carbon monoxide or H2, and we could do this with either reactant, if I take away one of my reactants, I'm going to see that the system is no longer at an equilibrium ratio because these numbers or one of these numbers is too small. And so I need to make more of those to kind of make up for the lost amount. And so we'll see that the reaction favors the reactant. So some of this methanol, CH3OH, will actually decompose into CO and H2 so that we get back to our equilibrium ratios. Remember, we're not stuck at a specific concentration of methanol, hydrogen, or carbon monoxide. What we're worried about is maintaining the ratio between them according to our law of mass action. So let's look at an example with this particular reaction. So we have some system here. We're at equilibrium. We have some ratio of carbon monoxide, CH3OH, and H2 molecules. Everybody is happy and stable. And then I add some additional carbon monoxide. So I've added 2 more units of carbon monoxide. And we see that now our ratio is messed up. because we're no longer at that equilibrium ratio. And so what has to happen is that some of that carbon monoxide needs to be used up. So we see that we lose a carbon monoxide. We only have 3 here. We lose 2 of our hydrogens because we go back to the stoichiometry of our balanced equation, and we've gained an additional methanol because, again, we're gaining 1 methanol for every CO and 2 H2s that are consumed. And so then we can get back to our equilibrium, and so we've reestablished that. The concentrations of carbon monoxide, methanol, and H2 are all different now, but all we're really worried about is the ratio. Does it still fit in with the law of mass action? Do we still get the same value of K? Now we can do the same thing by looking at the concentration of a product. So now what I want to do is look at what happens when I increase the concentration of a product. Basically, my system goes, wait, you're adding methanol, you're adding product, I have too much of that. I need to consume some of that, and so I need to use up some of that methanol. And the way I can get rid of some of it is actually going towards the left side, going towards the reactants. So if I add methanol, I'm going to actually favor the formation of reactants. We're going to increase this reaction rate in the reverse direction a little bit until we get to equilibrium, and then we get back to the point where our forward and reverse reactions are equal. If I decrease the amount of product, I take away some of my methanol, I'm going to see that the reaction is going to favor the right side, because if I remove methanol, and we're not worried about the logistics of how we're removing it, just say if we remove that methanol, we know we're going to have to compensate for that loss by reacting some of our carbon monoxide and hydrogen together to form some of the methanol to replace what was missing, but to more importantly get back to that ratio that agrees with our law of mass action, where we get a K value for that law of mass action setup. So here we're looking at an example. We're just looking at the addition of methanol. We could do the same thing with removing it, or just the opposite with removing it, but we're only worried about addition here. So we have our system at equilibrium here. We add methanol. So now we had 3 methanols initially. Now we have 5 units of methanol here. And so what we see happening is we have more methanol than we need. And so we've got to get rid of some of that. And when we do, when we use up our methanol, so now we only have 4 methanols, but every time I consume one of my methanols, I drive this reaction to the left, I see that I now have 2 more hydrogens. So here we have 3, 4, and here we have 6 methanols. And then I have an additional carbon monoxide. So I go from 2 carbon monoxides to 3. And so at this point, we are back at equilibrium. So here in the first panel and in the last panel, we are at equilibrium in both of those. This is representing the change that happened. And so even though we have different amounts of carbon monoxide, methanol, and hydrogen in the first and third panels, we are still at equilibrium because we have our equilibrium ratios are reestablished. So what we're going to do is, this is part 1. I am going to do a second part to this. I didn't want to have a video that was too long. And so we will go on in the next part to explore some of the other changes to the system.